Hello, hello. Here we are. It's that time of the week again. Here in Europe, it's almost the weekend. Other areas of the world are less lucky. I'm Luca Antiga, CTO at Lightning AI, and here with me is Thomas
Thomas, hi.
Viehmann.
Luca.
Hello,
This
hello.
time we
So
begin.
yeah, exactly. So let's do another step in our understanding of deep learning compilers and how the sauce is used made. So last week we went through a little bit of more details and we saw some code of how a computation becomes when it goes through a deep learning compiler. And we rehashed a little bit the importance of understanding that CUDA is asynchronous with respect to the CPU. We won't go back into that because we already described it a couple of times. And like broadly speaking, what happens when you want to generate kernels that are fused, generate programs that run on the device that represent multiple computation. And since you don't know ahead of time how many of them you need to put them together because the compiler decides it, then you need to have something that generates those kernels for you, a little robot that we drew last week. So what are we going into this week?
Yeah, I think we should be looking a bit more at what these deep learning compilers do. I mean, we saw that they produce these kernels for our functions that combine things, fuse things as you can. But really, we want to watch them getting closer to how the sausage is made. So we want to watch the
Yep.
various steps that a deep learning compiler takes in order to take your program and then make that into a series of kernels that run fast, right? Because that
Yeah,
is
yeah.
the ultimate goal, to not write them yourself, but to have the compiler do the optimization for you.
Yeah. So yeah, there's a few steps that the compiler needs to do in order to even understand what kind of things to generate, right? And but we are referring to multiple compilers, right? So deploying compilers. So there's not just one. We already mentioned a few, and there are more than we mentioned. Uh, but maybe this time we can actually take a stab at going back to our new Galu function
Yeah.
and seeing how we can run them the same function through the three like most popular, arguably most popular deep learning compilers. We'll start from Thunder, and then we'll go into Torch compile, and then JAX. We haven't shown any JAX code so far. And people may ask, well, what JAX is a framework, it's not a compiler. Well, actually, we'll learn a bit more about that. So let's dive right in. So we'll test something different this time. I will draw something, then we'll go through code, then I will draw something. We'll see. Hopefully
Yeah.
we'll get everybody done on time. Great. So first step is we go into Thunder.
Yeah. And
What is the map of the world for Thunder?
yeah, well, so we
Yep.
start with the program, obviously, that you have, the user program. So, for example, the new Yellow function, if you want. Um,
Yep.
and
This
now,
is going to be a few. This is written in PyTorch, right?
right, and the user will use thunder.jit to compile this into an optimized version of the function. And actually, with many of these compilers, when you do the call to JIT itself, it doesn't do anything. And we will learn a bit about the reason for this too. Um, but then if you run the JIT function, then things happen. And so what happens in Thunder is that uh, we actually built a Python interpreter in Thunder. And so the Thunder interpreter will run your function. Um, and it will, in order to not like cause the computation, it will replace the tensors with substitute objects, which we call tensor proxies, and it will replace calls to PyTorch with calls to Thunder, and it will produce a representation of the program, which we saw before too, which is like the trace. And actually, there also is a prolog trace, but for now, let's focus on the trace. And the trace contains the computation that Thunder wants to execute. And so it, again, is a series of Python or PyTorch functions that are called. But at the same time, it's our intermediate representation. And so we transform the trace in a series of steps until we transform it. We say transform for execution, where we decide like which bits should be handled by which backend, which for our case, what we saw last week was that NVFuser was the backend that basically took everything of our new Gillo function. But obviously, if you have a very complex network with, say, a transformer with linear layers and then attention, you will have typically multiple backends. Because you want to leverage all these specialized libraries like fast attention and cuDNN, but also you want to fuse the things just like we saw last week. So this will be, and this is in a way it's generic, right? The front end needs to get the user program, and then there's transformations internally. And then at some point, the backends come in. And one part where things might differ is like, are the backends still considered part of the system, at least when you casually look at it? Or how does that work? And how does the intermediate representation look like? But so maybe we
Yeah,
can.
so if we can, sorry, if we can split the world into macro areas, right? You have this part here, like here you have a function, right? This is your function.
Yeah.
And what we just said is very fundamental, and I want to make sure it's properly understood. So when you run thunder.jit, and that takes a function as an argument, nothing happens. That's a very cheap operation because we just wrap our function in something that will run instead of the function itself. So for example, if you have a function that allocates a super huge tensor, if you just call the function with the argument, then that allocation will happen on the GPU.
Well,
When
not
you,
only
yeah, go ahead.
not only will the allocation not happen, but actually when you call thunder.jit function, all it will do is it will return a function that essentially does two steps, like optimize the thing and then run it.
Yep.
And so nothing will happen there. But then if you call the JIT function for the first time, we have this front end that's responsible for like running through the thing, still not computing anything because it's the
Exactly.
front end. And then we get the trace as the first like object we get from the user's code, but which is our own representation.
Yeah, let's spend a minute to rehash this again. So we have a function, and if I call this function in PyTorch, and if I call this function with a tensor as an argument, that will execute kernels and allocate memory and all that kind of stuff, right? And produce
Right.
a result. That is PyTorch eager. So this is normal PyTorch. You just run whatever, and it runs at that time. When we call thunderjit, and this is common to like most compilers, when you call thunderjit, this function becomes another function, which is
Right.
called the jitted function, which is not really jitted. It's kind of a fake because it's not jitted yet. It's just a function that is not that function anymore, but it will probably execute the function at some point in time after a few transformations. Execute not that particular function, but it will understand what this function does and produce an equivalent computation that will produce equivalent results for equivalent inputs.
Yeah. So
So, and maybe it will also do it distributed, or maybe it will do it in a different uh, breaking up operation differently, or in the different numerical precision. So that is really important. So this jitted function is something I can call with an input. And differently from this situation here, where the function called with an input produces a computation, this function called with an input, which is the output of ThunderJIT here, right? It's a
right.
callable, so it's a function. And when I call it with an input, it will generate a representation, sorry, of the computation.
Yeah. Of
That is our
execution.
trace, right?
Yeah.
That represents what happens to inputs, and it traces what happens to metadata of the data. So it describes how the metadata flows. For example, if I take a tensor of shape 1010, it maybe, I'm expecting a tensor of shape 2020 of the same D type to be produced. That's the kind of metadata that I can compute through, and I can know what happens. But it will not allocate anything, and it will treat inputs like more symbolically, so to speak. Um,
Right.
and and it will record whatever happens to them. And there's a lot of depth to this, and we'll get more into this. And so this is what we when we say trace, this is what we intend. It's a representation of the computation before the computation actually happens. And then when we execute the trace through the executors, right? So there's another phase which is called execution, right? And this was acquisition. The execution will take the trace and execute it. And that is the time where tensors are allocated,
Right.
on the GPU, whatever, and kernels are launched and so on. In between here, you have transforms, and among the transforms, there can be different kind of transfer, but also the fusion that we talked about.
Yeah.
So let's
And
go into the code.
but
Yeah,
so
no,
it
go
could
ahead.
also be, and we will discuss that later, but you could also have like a model that will be quantized as part of the transforms. And then you might have a model that originally doesn't fit into your GPU memory. And after the transformation, it does fit, right? So that is very neat about this separation of phases. But you're right. Let's look at some code.
Awesome. So we go through this process with Thunder and then do our best to also show the same thing with other components.
Yeah, let me share my screen here. And obviously, I'm making a bit of an advertisement for Lightning Thunder. It's an open source project, so you can check it out. But we also use like the platform, the Lightning platform, in order to do our demos here. So I'm spinning up the studio. And the nice thing here is that it has everything installed. Like when I tried this morning how to get things out of JAX, actually JAX wanted cuDNN 8 and PyTorch wanted 9, and so it was a huge mess because I never use the envs as much as I should. And so the nice thing is that here it's all set up. So we can get right to it. And there's the old sessions, and I will spare you re-implementing the relo and so the Gelu that we had last week. So I will copy that to this week's session, And we started with this, but we also need, of course, import Torch and also import Thunder.
Can you
Because
make the editing a bit larger, maybe?
yeah, sorry, I need to remove
Oh,
this,
great.
right?
Awesome.
Okay.
Yeah, yeah.
So now if I have this function and we remember that it's a series of operations, we can JIT the function just like we just said. So J Gelu is Thunder JIT of the Gelu of the myGelu function. And so we see,
TH Thunder.
yeah,
Yep, TH.
we see that if I can type Thunder, nothing big happens. And if I like show JGello, it doesn't say a whole lot about what it actually does. But so under the hood, this is a thing that when you call it with some argument, this will actually call into Thunder. And so, and we can see that like the first iteration will be a bit slow. And if I do this again, it will be a lot faster. Well, for a small function, this is like not that much, but here we can see that the first time is a bit of a delay and the second time is instant.
Yeah, just to refer to what we said, right now, yes, it computed, but it went through two phases, right? When you call
Right.
Gelu X. One is the acquisition and the trace, and then it executed the trace. And the two things happen together because you want to have the illusion that it actually executes, but
Yeah.
it actually traced the computation like symbolically or whatever we want to call it, and then it took that and executed that.
Yeah. And of course, you could like acquire the compile data of JGelu and then you could split uh, split the two things by getting here the computation and inputs, and so this will do a lot of things, but this will do only the first phase and produce all our traces. But let's not look into it like this, but instead just look at the last traces. And the last traces, this might be a bit of a funny thing. We showed that last time too. It actually, when you had the diagram and you had the traces that get transformed, so this is a list of traces actually of the last execution. And the first one will be the trace as acquired by the program. Well, there's a dead code elimination pass, but basically it's the original program. And you can see here that, well, it includes the only line of our code. And then we see, well, yeah, it has the various operations, but there's nothing fused. But so this is the pure representation of this computation. And then as we go through the various transforms, things take shape. And so the first, well, here we don't have transforms in between, but so this is already the transform for execution. Um, and so this will assign each operation of the operations that we just saw to a backend. And so in this case, this will be the NVFuser backend. And so this is an NVFusion, and we can see like what has been in there. And there, like our compiler hands off this block to the NVFusion backend. And
Yeah.
yeah, and so we can be like inquisitive, and so if
Yeah.
I assign this here to a last trace, and I think we can also, if we go one step further, there will be another pass delete last used, which will always delete obsolete inputs. This is not very interesting when you only have one kernel here to call, but in larger models that can be
Yeah,
helpful.
of course, because it deallocates things that
Yeah.
it doesn't need anymore. So yeah, can we say that they're like some people refer to a compiler as something that generates a kernel, and it's not incorrect. Our like when we talk about Thunder, a compiler is something that will generate the computation, then an executor will then turn into a kernel. And they're like, concerns are a little bit different. And so when they ask me, oh, what is the difference between Triton, for example, and Thunder? They're on two different ends of the spectrum. Thunder is concerned with producing the description of the computation and transforming it. And then Triton, and as we will see maybe in the next section, is one of the ways you can turn a specification into a kernel.
Yeah, so if we want to align this here, Triton is more similar to the NVFuser in
Yep.
that it takes a specialized language, and actually Triton is a bit lower level than NVFuser. Um, it takes something that is a Python program, but which is essentially very rich in expressing CUDA uh, parallel programming paradigms, and then it produces actual GPU kernels. And so Thunder at this point, and we deliberately said, well, there's backends out there and we can hand off to them. And so one of our backends here is NVFuser. We also can use Triton as a backend. And so we say that we stop at this stage. But of course, if you just use ThunderJIT, you will not, if you don't debug, you will not see all the backends. And so it's a
Yep.
bit of a question where the compiler actually ends. But so
Yeah. Yeah.
here, for example, we can also see what in the end what NVFuser does if we want. So if we get the Python context, which is everything you need to know in order to execute this source, and it's a dictionary of local variables if you want. If we get the fusion here, we see
Maybe
that
we'll make it. Maybe we'll make it easier to access in the future. This is the state that it is now.
uh,
Maybe when some of you will be watching this, it will be a bit smoother.
yeah, we always try to make the best out of it. But so
Yep.
this is a fusion definition wrapper, and we can check what it last used as the NVFuser program. And so this is a NVFuser program if you want. It takes a fusion definition as input, and then it defines the computation that should be the fusion. And so we see that like the input tensors show up here, or the input tensor, and then we have the scalar, the factor 1/2 that we had, and this will be multiplied to x to the input, and then the other operations all happen. And in the end, we return this tensor here that has been the product of the 10H with the 0.5 times x. And so this is the fusion, and then NVFuser itself is a compiler too, and we can, for example, get the CUDA code for our input. I think I called it x up here.
Yeah, it
So
was X.
as in this tensor, which is like this argument here, and we have to make it a list because it wants all its inputs on a list rather than separate. And so modulo me using the print function here, you can see that this is a CUDA kernel, right? You have a global, which is a device function that is called from the CPU in this asynchronous matter. And so this is the actual CUDA kernel that NVFuser produced and will
And
run
this is compiled
several.
into an actual
Yeah,
executable thing on the. So it's compilers all the way down. So it's great because now we can compute like the whole thing in just one pass instead of like exchanging data back and
right.
forth.
And of course,
Awesome.
things like caching going on that we don't do all the expensive steps over and over again. But so this is basically the rundown from the initial function. Maybe we show your picture again. This is the rundown from the initial function that we started out with, that the user took, and then we saw that we had the digit fn, and then the transformations. We saw there was an eliminate dead code, then there was the assignment to the backends, and then we had the backends doing their thing, right? And here it was
Perfect.
user. And we could
Yeah.
peek
So how?
all
Yeah.
the way down.
Sorry. Yeah, exactly. So because at this point we took a diffuser, we said, okay, what is the computation that you had? And it had its own specification. And then we asked, okay, what is the CUDA code that you run? And here's the CUDA code. And we could access it. And it was generated on the fly. Now, the question is, how different conceptually is, for example, Torch compile?
Yeah, in some ways it's very similar in that you also have this front end. And in fact, Torch Compile and Thunder probably have the commonality that you can also feed entire PyTorch models into it. And so this will also produce like a compiled function. I think sometimes they call it the optimized module or so. Um, and so this again will launch the actual Torch compile magic, if you want, when you call it with an input. And so in Torch compile, the front end that produces the initial representation is called Dynamo. And it produces a fx graph as intermediate representation, which is again a linear representation of calls into PyTorch. And then this will be handed off to a backend, and the typical backend, if you don't like try to actively avoid it, the typical backend is called inductor. And so inductor will then, for example, in the case of our new Gello, it will generate code for Triton and then use Triton to compile a kernel, which is very similar to us using NVFuser. But Triton, we will see, is a bit lower level. So this goes then into PTX, which is what CUDA code also compiles to. If you want, it is a higher level assembly. There also is a lower level assembly SAS. But so PTX is actually intended to be platform independent across various GPUs from NVIDIA.
Yeah.
But yeah, so this is the chain that, and then this PTX kernel is translated into a SAS kernel or into GPU kernel, just like the NVFuser kernel, and then you run it on the GPU, right?
Yeah.
And
Do
of
we
course,
do we want to see it in action directly?
yeah,
Or do you want to add
obviously,
anything?
yeah, talk is cheap, right? We need to prove it now.
Let's do it.
Okay, so let me share my screen again here. And so this time, and we can reuse the function because it's like all Torch and we all like PyTorch. But so what do we do here in order to get at the graph? We do our own backend instead of using inductor. So my backend will be a function that takes a graph module and inputs, example inputs. And I've stole this basically from the Torch compiled tutorial. So it's not like I invented this, but so this graph module will actually have a graph, and you can print it with this print tabular. But you can also have a readable representation. Let's make a little space in between. And then you can also like do print readable. And who wouldn't like print readable, right? And now we need to, I don't know, probably the first time I wouldn't need it, but to facilitate running this several times, we will, and now that's the lazy importing that screws up the auto-completion and I'm completely lost. Okay, so this is like the lamest, we need to return something because we actually need to return a function that will run the thing and will be cheap and will just return the same thing. And now we can compile like our function with torch compile. And if I just did it like this and myGelo, that would do the real thing. But we want to do the fake thing, so we pass a backend parameter here, and that will be our backend. And so again, nothing happens here. But when we actually call the function with an input, we see, well, yeah, it computes it eventually, but we also see here, and now you can't appreciate the table maybe like this, but I need to like make
Yeah,
that
this is
small.
better probably. Yeah,
You can see the table here that has the various operations. So you have a thing that is called small and then pow because we need the third power, and there's another factor. And so this goes until you have the output. But so this is the tabular representation, and here's the readable one, which looks and is just like a PyTorch module. And you can actually copy paste this and run it. And so this is again our computation, but spread out. Instead of being on one line, it's spread across quite a few of them. And you can see also here that they're deleting the unused, the obsolete things by setting them to none. So this is very similar to what we have. So this is the first acquired program when you use the Torch compile, and this has been the Dynamo front end doing it. If we remove this, we could now try to, and now I'm in trouble. We can now try to get to the things that actually are generated by the backend, by inductor. But for this, we need some trickery. So we need to set a magic. At least that is the only way I found to do it. There might be better ones, but so you need to set torch compile debug to 1. And you need this before, to do this before loading torch actually. So I'm restarting the kernel here. And we define myGelo again. That's why I scrolled up here, not just to anger you. And so if we now compile this again, nothing happens. But if we call it now, and now this is without our own backend, but with a proper one, then we get the result. But we also have here that there's the inductor backend gave us a dictionary where it actually stored a lot of debug information, and I can like show what it is. And we see there's like fx graph, which is what we saw using our own backend here. But we also have the output code, which is the output of inductor, if you want. And so we can actually look at that by by just using cat, and it's not like the prettiest way to look at this, but here we are. And so this is a Python program again that you can probably use for debugging and run on its own. But so one of the things that is in here is a thing that actually compiles the Triton kernel. And so this is a typical, well, it's an auto-generated Triton kernel, but it is kind of typical in the sense that here the kernel loads the inputs, and then you do a computation that will typically be done in the registers, and then it stores the outputs. And you can see, like here, we're actually explicitly loading the thing and then storing the result. And in between, we have things like here's the pointer to the input and the offset, which is the program ID, which is the thread number on the GPU. So it's a bit lower level. NVFuser will hide that from you. But basically, this is like a representation of the kernel that it generates. And then this will go through LLVM and do its thing.
Yeah, so Triton has is nice because it kind of empowered a lot of developers to just ship their kernels alongside their modules. I think it's a testament to how important it is to provide good developer experience. Um, and so Torch Compile decided to adopt it also for their code generation because ultimately you need to generate this Python-like code. It's not exactly you can't run it
Yeah.
without interpreting it in Triton, but um, it has the concept of pointers and so on. It requires you to dig a bit more, but the barrier from me to from zero to experimenting with Triton is really low. So it's very nice.
Yes.
Um,
So
yep.
back in the old Torch script days, we would have the fuser that actually generated CUDA programs. But of course, this can be like less intuitive here. And so this is really something, a language in which you can relatively easily also write your own kernels with
Yep.
computations. The tricky thing is when you need like tricky memory accesses and stuff like that. Then you're like
Yep.
deep into the CUDA things, and you need to know them in order to write these kernels.
Yeah, there's a CUDA mode Discord for that.
Yeah,
But yeah,
and it's
so
starting again tomorrow, right? With a
yeah,
lecture from a
so
colleague from AMD. Um, Demonstrating a kernel generating library. So if you want to go really, really deep, check that out. Um, but so we also promised JAX. Shall we do the JAX,
yeah,
Luca?
let's do a little scribbling on Jack super fast. And then,
Yeah,
it'll take a few more minutes, but we go full circle here. So,
yeah.
um,
So you want to do the scribbling?
yeah, just two
Okay.
minutes. Just,
So
yeah, let
I'll
me do
give the
that.
screen to you.
Yeah, it's a bit of a dance, this episode, right? It's good. We're experimenting. We're never stopping innovating.
Yeah,
So,
obviously, if you
Jack,
leave comments in the YouTube comments, or if you write us on Twitter, we love to hear from you, right?
absolutely. Yeah, yeah, 100%. So, Jax, like a lot of people are saying, oh, Jax is so fast, and often it's fast. But why it is fast? There are a few reasons, but mainly because it's basically a compiler. It's a in between a framework and a compiler, or if it's a very thin abstraction on top of something like a compiler. So it's JAX lets you express computations that you can transform. It was introduced functional transfer for
Yeah.
programs early on, and then those transformed programs are then passed on to what? So let's see. So you have a front end.
Yeah, and if you obviously there has been things that have been stacked on top of JAX in order to recreate something like the PyTorch NN modular library. But so in the pure JAX thing, you have programs that look very much like the traces in Thunder or the FX graph, which is your starting point. So in a
Yep.
way, they took away the front end and started with a functional program, and then they have they represent this internally, or they avoid materializing it, but you can represent it as a JAX per, so it's a JAX
Yeah.
expression, and this will look like, well, it's their equivalent, if you want,
Yeah. It's a
of
mathematical description, let's
yeah.
say, more or less. Yeah.
And so this is kind of the IR, except that there's things going on the fly a lot. And then this generates a HLO, which is for XLA, which is the X, and JAX stands for XLA, which is a kernel generating library if you want. And of course, JAX has also TPU support through XLA. Um, and so here the XLA will then use LLVM to actually generate the code on the GPU. Very similar to what Triton does, right? At the
Exactly.
code generation. And
See,
so,
one of the things that it's famous in JAX is VMAP, right? Which means I have a function described for just one input, like new Jelu, and new Jelu, it's, I don't have the batch dimension there. I just write it. And then I have a VMAP transformation that will take this function, break it up into a sequence of primitives, all of which have a counterpart that is vectorized. And so this function gets transformed into another function of the same building blocks, but now the building blocks understand the batch dimension, for example.
yeah,
Sorry. And that is a vectorized version of the first function that will generate HLO operations that will then be compiled down to something that can run through XLA. So that is basically how JAX is fast. And so JAX is fast with the same like broad strategy that Torch Compile and Thunder use to actually be fast, right?
yeah. And actually, it looks very similar if we try to do that in code.
Yeah. So let's do that immediately.
So let me share the studio again. Um, and so similar to what we did with with PyTorch, we will set some XLA flags, magic environment variable, and because just setting it to one is like the easy way, we will now we get to choose the directory though. So JAX debug. And so we do this before importing JAX and NumPy. And I will just copy paste the myGello function to maybe save some time here. So if we take this new myGello function, and now it's the JAX Gello if you want, and then this needs to be JAX NumPy 10H, and now we can like take some numbers and pass that, and for this concrete input, we can see the intermediate representation, this JAX expression, by using make JAXPer. And so if I use this on the JAX Gello and I specify my input, and this is achieved in much of the way like we did above with our own Dynamo backend. But so this is our function again in a slightly different representation, right?
Yeah.
Um, and so we can also like go from there if we define the lowering. This will be we again take the JAX GELU and we lower it for the input that we have. And so one reason why you need the inputs in order to like start the compilation process is that it acquires all the metadata like the shape of the inputs. And this will like influence the compute layout on the GPU. And so this always needs to be there. And then the lowering can be compiled. And so this will be lowering.
How do you define lowering, like in
Uh,
common parlance? What is a lowering?
Yeah, so it is like a lower level representation. And so this will
Hmm.
be this HLO representation. And we can see now here, if we have this compiled, we can get the text. And so this will like look a lot, it's an HLO module here. And it will have the fused multiply, and you can like vaguely make out or I can vaguely make out that this is our function again, because here's the 10H and here's some addition that you do and multiplications, and then at some point you return the result. Um, but so this is like the intermediate representation. But then remember that we had in our temp directory, we had the JAX debug. And we see here that it has like a whole lot of files that will not go into like the LL here. This is the actual LLVM representation. If we look at this,
And LVM is the famous compiler, right?
right, it's
Um,
the compiler system, if you want, which
Compiler
has
system is not the compiler. It's
all
a
the
system to
backend.
build compilers. Yeah,
Yeah,
a lower level, low level virtual machine.
and it's also what powers Clang, for example, the C
Yep.
compiler. But so here you see that this is like an LLVM module, and this is like very low level already. But so then you also have the PTX, which will be like the real thing, right? And this is actual like generated by the NVPTX backend, and this is the like device independent assembly for the CUDA kernel that it generates. And so we went
Fantastic.
here all the way from user function to PTX, which will then be like translated into the actual machine code in order to run it on the GPU.
Perfect. I think we got what we promised we would get. So we took a simple function, we traced the journey of that function down to, something that can run on a GPU, both with Thunder, or with all the compilers that we targeted, Thunder, Torch Compile, and JAX, and we understood that fundamentally there are some commonalities because ultimately you need to get from your function to something that runs on the GPU. So the journey is similar, but details are very important and details differ. And so we'll get into more specifics in the next few episodes. But for the time being, I think you should just take a break and enjoy your weekend, I guess.
Yeah, you should enjoy your weekend too, Luca.
Yeah.
And see you again next week, same time.
Yes. Same time. Thank you so much. Bye, everyone.
Bye.